Arduino is often introduced through a single familiar shape: an Uno on the desk, a Nano resting between breadboard wires, one LED, one button, one small sketch beginning with setup and loop. And that beginning is useful. It gives the hand somewhere simple to rest while the mind learns how a signal becomes a response. But the Arduino logo is a doorway, not a border. Beyond the official catalog, there are compact boards made around STM32, Raspberry Pi silicon, modern AVR parts, enhanced AVR-like chips, and custom controllers designed by small companies or individual engineers. Some look like a Nano, some have 40 pins, some arrive with USB-C, 2 processor cores, programmable I/O, or more memory than an Uno can hold. And still, inside Arduino IDE, a sketch may begin in the same calm, recognizable way: pinMode, digitalWrite, serial. One familiar surface, opening onto very different silicon. In this lesson, we begin with the bridge that makes that possible. The phrase Arduino compatible sounds simple, but it can describe several different kinds of compatibility. The first is source compatibility. Code written with common Arduino functions can often be compiled for another board. A sketch may still contain delay, analog read, wire, SPI, and the same 2 ceremonial functions, setup and loop. The second is physical compatibility. A board may copy the Nano outline, its header spacing, or some familiar pin labels. That can make a shield, a cable, or an old prototype fit more easily. The third is electrical and operational compatibility, and this is where the quiet differences begin to matter. A board may use 3.3 volt logic instead of 5 volts. It may upload through USB, a serial bootloader, UPDI, SWD, or a separate debugger. Its pins may have another meaning. Its timers may have another rhythm. Its memory may be radically larger or much smaller. So Arduino compatible does not mean identical. It means that a common language has been prepared, while the hardware beneath that language still deserves to be known. An Arduino sketch is usually portable as source code, not as a finished binary file. A compiled program for an ATmega 328P contains AVR machine instructions. An STM32 uses ARM instructions. RP2040 and RP2350 boards can use ARM instructions, and RP2350 can also boot RISC-V firmware. Those instruction sets are different languages at the lowest level, so the IDE does not simply carry one finished program from board to board. It rebuilds the sketch for the selected target. The familiar function call is translated again. digitalWrite becomes the correct operation for a particular port and pin. Millis becomes a timer arrangement chosen for that chip. Serial becomes a hardware UART, a native USB serial interface, or another serial path selected by the board definition. The sketch remains the visible intention. The translation changes underneath it, and once you can feel that distinction, the rest of the Arduino ecosystem becomes much easier to read. The name for that translation layer is often an Arduino Core. More precisely, Arduino IDE installs a platform package. Inside that package are the pieces that make a particular hardware family usable from the Arduino environment. There is core code, the implementation behind familiar functions such as digital I/O, timekeeping, serial communication, interrupts, and startup. There are board definitions, the selected microcontroller, clock settings, memory layout, upload method, and build options. There are variants, small files that map friendly Arduino labels, such as D13 or A0, onto real pins of a particular board. There may be target-specific libraries, compiler settings, debugging support, programmers, bootloader tools, and recovery tools. So a core is not a tiny program living inside the board. It is part of the software environment on the computer, a carefully prepared path from sketch to machine code. The board receives the result only at the end. First, the package understands the hardware. Then the compiler gives that understanding a precise form. You can picture the build process as a sequence of 5 layers. First, there is your sketch, the visible idea. Second, the selected board definition tells the IDE exactly what the target is: its microcontroller, clock, memory, pin variant, and menu options. Third, the Arduino Core supplies the hardware-aware implementation of the common API. Fourth, a compiler and linker build the sketch, the core, and the required libraries into a firmware image for that processor architecture. Fifth, an upload tool carries that image into Flash through the method the board understands: USB serial, DFU, SWD, UPDI, ISP, or a vendor-specific bridge. The movement is quiet but exact: sketch, definition, core, firmware, upload. And if one layer does not match the real board, the smooth upload button can become a closed door. That is why experienced work begins not with guessing, but with selecting the exact board, exact chip, and exact upload path. This is also why a platform package cannot erase the physical limits of a board. It can make a foreign microcontroller feel familiar. It cannot make a 3.3 volt GPIO safely accept every 5 volt signal. It cannot place more SRAM inside a small chip. It cannot give native USB to a controller that has no USB peripheral. It cannot turn a timer register written for ATmega328P into the register layout of STM32, RP2040, LGT8F328P, or ATmega4808. Portable Arduino code travels best when it stays close to the shared API. Direct register code travels only when the author has deliberately written it for the new hardware. The same is true for libraries. A library using wire.begin and ordinary digital I/O may move gracefully. A library that assumes AVR timer numbers, AVR EEPROM behavior, or the old AVR interrupt layout may stop at the boundary. That is not a failure of Arduino. It is an honest signal from the hardware. The familiar surface has reached a different interior, and you can learn to hear that signal before it becomes an error message. There is one more layer worth holding gently in mind. Recovery. A board is not defined only by the easy, successful upload. It is also defined by how you return when the sketch disables USB, takes over a serial port, enters a bad sleep state, or simply contains a mistake. On a classic Nano, recovery may mean a serial bootloader or an ISP programmer. On a modern AVR, it may mean UPDI. On STM32, SWD through an ST-link is often the direct path back into the chip. On a Pico, Bootsel can expose a USB mass storage route, while SWD remains available for deeper debugging. The exact route changes, but the engineering habit remains the same. Before the first experiment, know how to enter, know how to return. That knowledge removes a surprising amount of fear from unfamiliar hardware. You are no longer touching a mysterious board and hoping it obeys. You know its language, its doorway, and the path back through the doorway if the first attempt becomes tangled. So now the larger picture is beginning to settle. Arduino is not one processor. It is not one voltage. It is not even one exact collection of boards. It is a development model, supported by platform packages that connect a shared sketch style to many hardware worlds. The core creates the translation. The board definition gives that translation a body. The upload tool opens the correct entrance. And the real circuit still asks for precision, voltage, pins, memory, clocks, libraries, and a recovery path. In the next part, we will look directly at the core packages installed in the Arduino IDE menu. Some are official Arduino packages, some are maintained by independent developers. Some are wide bridges to enormous chip families. Others are narrow, elegant bridges to one small line of controllers. You do not need to memorize them all at once. Just let the pattern become clear. One familiar sketch, one chosen core, one exact board, and then a signal that knows where to go.